Welcome to our second video in our three-part series on backpropagation. In this video, we will apply the backpropagation algorithm to this equation. One of the equations that we saw in the last video was this: y equals 3 times x plus 2 squared. And we broke it down into its constituents like this: z1, z2, and y, and finally we drew the compute graph. Now in this video, let's draw the backpropagation graph for this compute graph. Now the backpropagation graph looks exactly like the compute graph, except for two key differences. The first difference is that it flows in the opposite direction. So what do I mean by that? Well, these arrows will be drawn like this, in the opposite direction. And the second key difference is that the variable nodes, so for example z2, will be replaced by their gradients, so dz2. And the operation nodes almost don't matter. So now let's go back further. So we go back, and now we replace z1 with the output that it produces, so that's derivative of dz2 with respect to itself. Now let's continue on the backward journey. X is replaced by its output, so derivative of dz1 with respect to itself. Now we could also come to this node and we could say, hey, I'm going to replace 2 with the derivative of dz1 with respect to 2, but that's nonsensical because 2 is a constant. So we don't do that for constants. We only do that for variables. One final thing. What is the last node, the last leaf node, y replaced with? Well, we'll just replace it with dy dy. Now, why did we do all of this? We use backpropagation to find the derivative of one of the leaf nodes, right, with respect to one of the root nodes. Now in this case, it so happens that the only leaf node we have is y, and the only root node of any consequence is x, because the other two root nodes are constants. So we want to now find the derivative of dy dx, right? dy dx. And that is simply the product of all the derivatives that we encounter along the way. So dy dx, we'll start with dy dy times dy dz2 times dz2 dz1 times dz1 dx. And if we just plug in these values, we will get the derivative of dy dx. Now you'll notice that this is nothing but the chain rule of derivatives in action. But doing it via backpropagation graph makes it that much more easier for more complex equations, as we'll soon see. So now let's start replacing the values. So dy dy is replaced with 1 because that's kind of a no-op derivative. dy dz2, I'm sorry, this should be c2. So let's see, dy dz2 is simply 3. So replace this with 3. dz2 dz1, well, dz2 dz1 is simply 2 times z1. So we'll replace it with that. And dz1 dx, so dz1 dx is simply 1. So we replace it with that. And what we get is 6 times z1. z1 is x plus 2, so 6 times x plus 2. Now this is not a very hard equation. If we wanted to find the derivative of y directly, all we could have done is say, oh, dy x equals 2 times 3, so that's 6 times x plus 2, and the derivative of x plus 2 is 1, so it's 6 times x plus 2. And this works because this is such a simple expression, but for more complex expressions, doing it the backpropagation way and applying the chain rule like this is a lot more tractable than doing it for the entire equation at once. Now that we've seen the underpinnings of how backpropagation works, let's see it in action in PyTorch. So here's our equation, y equals 3 times x plus 2 whole squared, and dy dx equals 6 times x plus 2, right? So for x equals 1, dy dx is going to be 6 times 3, which is 18. So we'll see this in action in PyTorch. And if you have not installed PyTorch, head over to pytorch.org, and they have instructions of how to install PyTorch for your platform. So all I need here is import torch. Let's define x as a tensor. The requires grad equals true is telling PyTorch that I will eventually create a backpropagation graph, and I will need to find the gradient of x, which is the derivative of the output with respect to x. That's what, when we say gradient, that's what we mean. Y, let's define the equation, is 3 times x plus 2 whole squared. When you do this, when you define y like this, what PyTorch did was, behind the scenes, it created the compute graph. So we didn't have to do anything for it to create the compute graph. However, when we want to create the backpropagation graph, we have to tell PyTorch to do that. And the way to do that is to call the method backward on any node from which you want to create the backpropagation graph. So because we're saying y.backward, it's going to create the backpropagation graph starting from y and going all the way to the root nodes. If I would have created some intermediate variable and then done a backpropagation graph, dot backward from there, it would have just created the backpropagation graph for this section. But here we are just doing it from the leaf node, which is y, all the way up to all the root nodes. So let's run this. And now we want to get the gradient of x. Remember, when I say gradient of x, it simply means the derivative of the output with respect to x. And to do that, all we do is x.grad, which is 18. Now in machine learning, we rarely, if ever, work with just scalars. We usually work with different types of tensors. Either they're vectors or matrices or some multidimensional tensor. So what happens if our x is a vector of size 3? And each element is represented by x1, x2, and x3. Well, assuming the same equation, y is also a vector of size 3, with each element being 3 times the corresponding element of x plus 2 squared. And then what is the gradient of the vector x? Again, the gradient of the vector x means the derivative of the output with respect to the vector x is simply also a vector of size 3 with the corresponding derivatives, right? So it will be 6 times the corresponding element of x plus 2. Okay, so now let's see this in action in PyTorch. So as before, we'll create the tensor of all ones. We set the value, we set requires grad equals true. Again, as before, nothing changes. Y equals x plus 2 squared. And again, as before, it will create the compute graph behind the scenes. And now when we want to create the backpropagation graph, and we say y.backward, it's actually going to give us an error. So let's see what that error is. What the error says is grad can implicitly create it only, and it's getting cut off, but what it's saying is only for scalars. And to understand what this means, let's go to the documentation of backward. So here we're looking at the documentation of torch.tensor.backward. And look at the first parameter. It says gradient equals none. And it's saying gradient with respect to the tensor. So what it wants us to do is provide it with something, some output, derivative of some output with respect to y. Well, y is the final leaf node. There is no other output. So this is where we use dy dy. Okay, so let's define dy dy to be a tensor of ones, because that's kind of a no-op derivative and it will always be 1, and its shape is just like y, right? And then give dy dy like this, and now it works. So now it has created the backpropagation graph for us. If you're curious, dy dy is simply all ones. And now if you want to calculate the gradient of x, all we do is this, and just like before, it's 18, 18, 18, right? Because x1, x2, and x3 are all ones. You can try out different values. Let's say we make this 2, we make this 3, then we expect the first element to be 18, the second element to be 2 plus 2, 4 times 6, 24, the third element 3 plus 2, 5 times 6, 30, right? So let's just run this again. There you go, 18, 24, and 30. So there you have it. We applied the backpropagation algorithm to the first equation, and we'll do the second equation in the next video. See you there.